In this video, I'm going to calculate the Sagnac effect for a Sagnac ring illustrated here, consisting of a circular path, a photoelectric path with a source of photooptic path with a source of electrons, which emits electrons in opposite directions along the ring, which emits photons in opposite directions around the ring, and then when the photons arrive back at the beginning, they're reflected out onto a screen. Now, the photons originally are correlated, and the effect that Sagnac looked for was the photons arriving out of phase if the ring were rotating with angular velocity omega. Now, the naive analysis that's been done all these years for the ballistic theory is to say that as alpha approaches zero, the velocity of the photons, the absolute velocity of the photons, is c plus v in this direction and c minus v in that direction. In which case, now, what we have now is a photon with absolute velocity c plus v running after a ring that's rotating at angle omega, or if we uncurl the ring into a straight line, then it's the same problem as a train going at velocity v that's being chased by a photon going at velocity c plus v. And that calculation says c plus vt is equal to L plus vt, from which t is equal to L over c. Now, in the opposite direction, where the photon direction is opposite the ring rotation, we have this situation where now v is in the opposite direction and c minus v is in that direction. Then c minus vt is equal to L minus vt, t equal L over c. Now, in a previous video, I showed that this was wrong and that you could get the classical calculation using ballistic theory by taking a frame attached to the ring. And then after that I said, well, now, I mean, just to be sure and logically, I should get the same result if I calculate the Sagnac effect with respect to an inertial frame of reference. And I couldn't do it. And I worked at it for months and months, and I went through notebooks, constantly, all these notebooks with circles in them, and finally I got it. And that's the subject of today's video. I'm going to calculate the Sagnac effect for a rotating ring using a reference frame attached to the inertial frame. All right, now the situation is geometrically the following. I have the velocity c of the photon emitted at an angle alpha. Then I have the velocity v of the ring from this point, which is horizontal. So the resultant velocity is c plus v. All right, now, using this, at alpha is the angle of c, beta is the angle between c and c plus v, and the perpendicular to these two directions make the same angles. Here's alpha, and this is beta. That's a little geometry that you're just going to have to convince yourself of. All right. Now, from the geometry, we have that h is equal to c times the sine of alpha. H is equal to c times the sine of beta. Right. H is equal to c times the sine of beta, which is equal to v times the sine of alpha. Now, if alpha and beta are very small, sine alpha is approximately alpha, sine beta is approximately beta, from which you get that beta, if you make these substitutions, you get that beta is v over c alpha. And then from that, you get that AF is equal to 2r, AF is 2r times the sine, AF is 2 times r, 2r, it's twice r times the sine of AF sine of this angle here, which is alpha minus beta. And that's equal to 2r alpha times, substituting beta equal v over c, alpha times 1 minus v over c. Now, the secret and the crux of the whole matter is what happens as alpha approaches 0. In the naive approach, as alpha approaches 0, c plus v approaches a tangency or becomes tangent, and the absolute value is c plus v. Now, I purposely wrote as alpha approaches 0. I didn't say alpha equals 0. When alpha equals 0, then the tangential velocity, the velocity at this point of the ring is c plus v, and it's tangent to the ring, which is this situation here. However, physically, alpha can never equal 0 because the photon is going around a ring, and as it goes around the ring, it's skipping, it's making its progress by a series of many arcs, many little segments around the ring as it jumps from molecule to molecule. It can never, the situation that the photons are traveling around the ring perfectly tangent to the ring is a physical impossibility because the ring is not continuous, it consists of molecules. Right. With that understanding, as alpha approaches 0, the velocity is going to be c plus v, but you're always going to have this factor fb, due to the fact that the c and v are never exactly in the same direction. So then if you correct, so then AF is, using this correction factor, 1 minus v over t, AF over AB equal 1 minus v over t, correcting for AF over AB making the correction to the original c plus vt, we get that as alpha approaches 0, the absolute velocity is 1 minus v over c times c plus vt, and that's equal to L plus vt. So we're just applying this correction factor for the fact that alpha never is equal to 0 to c plus v. We get 1 minus v over c plus vt equal L plus vt. And that's the hurdle right here. Once you get past that, everything up to here and beyond this is the hurdle right here. If you understand that, you understand the Sagnac correction factor, as I call it. The fact that, and this comes from the fact that you're going around a curve. All right, so if you expand this, you get c plus v minus v plus v squared over c. These terms cancel, and you get ct equal L plus vt, which is t is equal to L over c minus v, which is the result that you get if you assume that the absolute value in the inertial frame of the photon on the rotating ring is equal to c, which is, I guess you might call that the Einstein assumption, but that's incorrect. That c is a result of the curvature of the path. All right, now I did it again just as a review of the geometry that happened here. I did it again for the case that the ring rotates clockwise and the velocity c is opposite to the direction of the ring. Then we have c at the angle alpha. We have c plus v here. Then we have h, and this angle is that angle, which is alpha again. So that now we have h is equal to h is equal to c plus v as this again, as alpha approaches 0, c plus v are in the same direction, close to the same direction. H is equal to c plus v times the sine of beta, which is equal to v times the sine of alpha. This angle here is alpha, alpha. From which beta, again with alpha and beta approaching 0, but not equal to 0, beta is v over c plus v times alpha is v. You just neglect v compared to c, is equal to v over c times alpha. With that, just reading off the geometry from here, we get this, that AF sine alpha plus beta, 2r sine alpha plus beta. Sine of alpha plus beta when alpha and beta are small is alpha plus beta, beta is v over c alpha. So you get that AF is 2r alpha times 1 plus v over c. And then, again, AF, as alpha approaches 0, 2r alpha is AB, and AF over AB equal 1 plus V over C, and that now is the correction factor due to the fact that C plus V never becomes completely tangent. As long as you have a factor V, B and F are always going to be slightly different, and that's the correction. Now, applying this correction to this equation, it becomes 1 plus V over C times C minus VOT equal L minus VT. And if you expand it out, again you get C minus V plus V minus V squared over C cancel, you get CT equal L minus VT, which makes it look like the absolute velocity is C, but it's not. It's a result of the ballistic or emission effect for the photon. So then we have T equal L over C plus VT, and the standard, the standard result for the time difference between the arrival of the photons at the source, delta T, is the time around in one direction minus the time in the other direction, which is 1 over C, L over C minus V minus L over C plus V. And then if you multiply that, if you get the common denominator, you get 2LV over C squared. I'm not going to go through elementary algebra here. 2LV over C squared. Now L, the length of travel, L, is 2 pi r. It's the circumference of the ring. So L is, so we have 2 times 2 pi r. V is r omega divided by c squared, which becomes 4a omega over c squared, which is the textbook accepted formula for the time difference between the arrival of the two photons in the ring. And to get delta L, the offset of the two photons, it's simply delta L is equal to C delta T, so it's 4a omega over C. I ran out of space, that's why I left it at that. All right. Now, as a review, I'm just going to briefly, I'm going to go over in a more concise manner, the original calculation that I did for a frame attached to the ring. In that case, with a frame attached to the, suppose the ring is a train in a circle. There's the end of the train, the beginning of the train. And I'm standing at the source of the photon. So the photon, with respect to the ring, the photon is emitted with velocity c with respect to the ring. So now, if I look at a stationary ring and the photon emitted with velocity c, with respect to the ring, then the situation I have is that a photon is moving at c inside the train, and whose length is L is 2 pi r, and I get Ct equal L and T equal L over C. So there is no photon effect. However, the photon track, and this is the critical point for doing the analysis with respect to the ring frame, the photon track is not stationary. The photon track is stationary in an inertial frame. So if you review that, and if you look at it from a frame rotating with respect to the inertial frame, you're going to see that ring rotate. So initially, the photon is ejected with velocity c in that direction, then it moves along here with velocity c, and at the same time this track is rotating, so it winds up at point F. Now, the amount that this edge that B rotates is equal to this distance here is equal to omega times t, because the perpendicular to the two tracks rotates at an angular velocity omega, and the endpoints of the end, these lines here rotate at the same omega, and that makes BF equal to R omega t. That's it. That's straightforward. There's no hanky-panky there. All right, so now we have that AF is equal to AB plus BF. AB is equal to AF is equal to AB plus BF. So that AF is equal to CT plus R omega t. And if I divide that by the time t, I get C plus V is equal to, and R omega t is V. I get C plus V is equal to V circumferential. Right, now that I have the circumferential velocity, I have the velocity, the circumferential velocity with respect to the train, not with respect to inertial, not with respect to the inertial frame, with respect to the train. I can now simply write that if I'm in the train, looking from the viewpoint of the train, I see the photon emitted with the velocity C plus V. I have C plus Vt is equal to L, from which T is equal to L over C plus V, which is exactly this case here, where omega was rotating clockwise, and the path was stationary. Now omega is rotating clockwise, and the path is rotating clockwise, and the path is rotating in the opposite direction, counterclockwise. So if I do this for the other opposite direction, I get T is equal to L over C minus V. So I get exactly the same thing that I got here. So to sum up, the Sagnac calculation for a rotating ring based on based on an inertial frame and on a frame fixed to the ring give exactly the same result for the Sagnac calculation, which is this here. And that's a classic result with a completely logical explanation instead of all the explanation I've seen. They simply assume that they simply assume that that the absolute velocity here is c, and then everything follows. Well, that assumption is right in the sense that it's a result of the ballistic theory or the emission theory. Good luck. Thank you.